Swayam Prabha. Digital India. Educated India.
Hello, welcome to NPTEL NOC, an introductory course on Point-Set-Topology Part-II. So today we take up another topic in this chapter, namely filters. So today, module 30, we will just study basics of filters. Given a set X, it is easy to see that the collection of all nets in X is too large and indeed not a set. On the other hand, filters are going to be subfamilies of power set Px of X, and hence the collection of all filters on X is a set. We shall see that filters will do, quote unquote, all the jobs that nets were invented for, okay, and some more through the concept of ultra filters and ultra close filters. These concepts or anything parallel to that is not available for nets. So that is one way of looking at nets versus filters. So filters seems to have an advantage. So that is one of the you may say justification for studying filters now, after having studied nets quite thoroughly. Okay, let X be a set. By a filter or F, I will be using this F prime and so on, this notation for filters. Filter F on X, some people may say filter F in X also, no problem. We mean a non-empty subset F of the power set Px satisfying the following three conditions. Empty set is not a member of F. Please note this one, this is very important. F is closed under finite intersections. This one is familiar to you, like in a topology. Okay. A contained inside B contained inside X, these are subsets of X. A is in F implies B is in F. All supersets of a member are also inside F. This is the condition. So such condition was not there when you are studying topology at all. Okay. So similar to conditions of topology, we have these three conditions. Only these two, this is finite intersection is there. Okay. And strongly empty set and X were there in the topology. This one denies that empty set is there, empty set should not be there. So this is the important definition. Usually the name filter comes from the property 3. 1 and 2 seems to have been put there as an afterthought. Okay. This property 3 generalizes many areas, and in many such areas also people use the word filters. Okay. So there the definitions will be different in algebra, in geometry and various things we can use that. Note that 1 and 2 together imply that F has finite intersection property. I will be using this one again and again. What is the meaning of finite intersection property? Given any set of finitely many members of F, their intersection should be non-empty. First of all, 2 says their intersection is a member. Closed under finite intersection means take finitely many members here, take the intersection, that also is a member. But that member is non-empty. So together they imply F as finite intersection property. Since every filter, okay, is non-empty, okay, you see, started with a non-empty subset of F. In the definition of filter, I have put a non-empty subset. As soon as a non-empty subset is there, X will be also there. Okay, so I don't have to put that condition. X is there, empty set is not there, and X is there. Okay. Also, compare the conditions for a topology and for a filter. This is what I have done already. I will repeat it. A topology always contains both empty set as well as the whole set, whereas property 1 says that empty set is not there. The second one is common to both of them, topology as well as filter. Third is much stronger than the third property or whatever is, namely arbitrary union of members of F is of tau is inside tau. So that you have, looks like that you have replaced it, but this is very strong. Even if one member is there, okay, supersets, there will be union of those, they will be there. So this is much more stronger than being a topology. All right. We have seen that X is there. Okay, the total space, total set X is there for all filters F inside X. This implies that the smallest and simplest filter is singleton X. You just take singleton X, okay. Of course, X should not be empty set. X itself should not be empty set. Then singleton X is a filter, okay, because it has finite intersection property and there is nothing more bigger than that. So this is all. On the other hand, the collection of all non-empty subsets of X is not a filter unless X itself is a singleton. You see, in the case of topology, there was this singleton X as well as empty set. If they are there, that was an indiscrete space. If you allow all the subsets, that is a discrete space, right? Here we cannot allow all of them at all. Throw away the empty set. Yet whatever is left out, that will not be a filter unless X itself is a singleton. Because as soon as X has 2 points, you can take singleton X, singleton Y. They will be disjoint, but their intersection is empty, right? So that is not allowed. Finite intersection property will not be valid, right? Or property 2 here will not be valid if 2 disjoint sets are there. So that is the important thing you have to observe here. Okay, so this is one example. Let us see some more useful examples. Given any non-empty subset of X, look at the family Fa. This notation we will use again and again. Okay, of all subsets B of X which contain A, including A of course, this filter is called an atomic filter with A as its atom. One single element and all its one single subset and all supersets. Okay, so that is a filter obviously, and that filter is called atomic filter with A adds its atom. Now there is a notational thing here. If A is a singleton A, I won't put that bracket here. I'll just write F little a for F capital A. Now suppose you have an infinite set. Then there is just like in the case of topology, there is this cofinite filter. What is it? Don't take empty set, but take all other members of tau, this cofinite topology, namely all subsets such that their complement is finite, okay, cofinite subsets. So that will be automatically a filter, because first of all, if you take any two members, their intersection has to be non-empty, because both of them have a complement is finite, and you are working in an infinite set. That's important. Okay, the moment one is there, anything which is bigger than that will also have cofinite, it will be complement will be finite, so that is also there. Okay, so this is an example, not very useful or anything, just to make the concepts of filters a little more clear what is happening. Given a net S from D to X, so D is a directed set, S is from D to X, take any element A inside D and take the section SA, set of all SB such that B follows A, that or B is bigger than A, whatever you want to say, including A also. Okay, look at that. That is the definition, little s A here. Now look at this S is coming here. I am defining this Fs. Fs is all subset A of X such that there exists an A belonging to D such that this SA is contained inside A. Okay, including the equality is allowed here. All SAs will be there and their supersets will be there. That will be very easy to verify that itself is a filter. Okay, so this filter is called the filter associated to the net S. So I am bringing net and filter together here via this concept, okay, namely S going to Fs. Okay, this filter is called the filter associated to the net S. Okay, it is important because it plays the role of a one-way bridge from nets to filters. Why I am calling one-way? I don't know any nice way of going from filters to the nets. This way it is very nice, very easy work. Okay, so this one-way bridge is there. We shall have an opportunity to elaborate on this point. Why this important to a bridge? Okay, just by having such a function doesn't make much sense. So we will see why this is important. Here is one more example. In a topological space, take the family of all neighborhoods Nx of a point X. Given each X, you take the neighborhood of, okay, that X is fixed here by the way. This Nx itself is a filter. Okay, finite intersections, all of them will contain X, so it is non-empty. Anything bigger than that will be a neighborhood, so automatically they are all there and so on, right? And the whole space is there. Empty set is not there because empty set cannot be a neighborhood. All right. So you may say that this simple example is the role model for the topological theory of filters. Remember, the filters were defined without any reference to topology. There was no topology on X. But what we did was we compared it with the concept of topology also, that's all. Okay, so far there was no topology. If this example is the first example wherein topology of X is used to get a filter, and this filter is the filter which guides us as far as the topological theory. What does it mean by this one? Convergence and such things. Okay, for this we have to refer to this one. Let us see how this comes. Now, before taking up the study of interaction of filters with topologies, let us proceed our study of filters in a fashion similar to study of topologies, but independent of any reference to particular topologies on X, except noting down certain similarities between this and dissimilarities between this and the concept of topology. That's all. Okay. So we will take more examples also later on. All right. So first notice that if F alpha is a family of filters on X, then their intersection is a filter. You had a similar theorem for topologies. That is what I wanted to say, that we are comparing. Intersection of arbitrary families of filters, all of them are, remember, they are subfamilies of Px. So whole thing is make sense. What is the meaning of this? Take all subsets A of X, okay, such that this A is inside F alpha for every alpha. So that is the intersection of this family. That is a filter. Of course, empty set is not in any of them, so it won't be here also. All right. So you can easily verify that this is a filter. However, even the union of just two filters may fail to be a filter, because one filter may have an element of some set, another one, their intersection may be empty. Right? You don't know that. There is no hypothesis. So that is one reason why union of two filters may fail to be a filter. This was there in topology also, but luckily, if we have two topologies, you can take the union and then generate a topology containing that. Even that will not be possible in the case of filters. Okay. So however, we would like to do that kind of thing here, namely generating filters, just the way we have done generating topologies. Okay. A subfamily B of a filter is called a base for F if for each A inside B there exists a B belonging to B such that B is contained inside A. This is very, very similar to the definition of a base for a topology. There, for each X and a member containing that, there must be something B here. Here there is no reference to the point at all. For each A inside F, there must be a smaller B which is inside this curly B. Okay. In other words, take a member of B, curly B, take all supersets. They are allowed to be inside F. That is the construction here now. That is where we are leading towards. So we have made a definition of a base here. For example, the entire F is a base for itself, just like in a topology. Okay, the entire set is a base. So this definition of a base satisfies similar to the conditions of what we have done in the for topology, but it's much more general. Okay, for example, the base for a topology had to have this property, namely union of all members is X. That X, it must be a cover for X. No such condition is here. Okay. All right. Let us look at some examples. Any local base at X belonging to X, where X is a topological space now, is a base for the filter Nx. So this was one of the important filter, right? So you don't have to take all the neighborhoods. You take a base in the usual terminology of a local base in the topology. That will be a base in the sense of filter. It's a base for the filter, right? Because what is it? If you have a base for every neighborhood of X, there will be a member in the base, and that condition is satisfied. That is what it is here. Over. A base determines a unique filter in the following way. The family of all sets which contain some member of B. Okay, you see, there may be a filter here. B is a base for that, but this filter, what I am generating, may be even larger. Okay, why? Because the family of all sets which contain some member of B is taken. In particular, if I start F a filter and a base for it, okay, the filter generated by that, determined by that, may be even larger. That's all. So it is clear that if we start with a non-empty family B which satisfies 1 and 2, then it defines a unique filter for which B is a base. Okay. Also, it is clear that different bases may give rise to same filter. If give rise to means I have described a method here. Okay, generating or whatever you want to call, taking all the members which are supersets of some member of B. Okay, the following result gives a complete picture now. A non-empty B contained inside Px of non-empty subsets of X is a base for some filter on X if and only if B1, B2 belong to B, there exists B3 belonging to B such that B3 is contained inside B1 intersection B2. You see, this is again similar to the base, similar to topology in the topological space, except here no reference to the point. Okay, given any two things, intersection should contain another member. Intersection itself may not be there. Intersection should contain another member from B3. Okay, so once this is there, okay, because they are non-empty, right? So finite intersections will be also non-empty, and finite intersections you can go B1, B2, B3, B3, B1, B2, say B version. Then you keep taking further and further. Okay, intersections of that. If B3, B4 is there, then you can take B5 which is contained in that one and so on. So this is very easy to prove by induction. So non-empty family B of Px is non-empty subsets of X is a base for some filter if and only if for B1, B2 belong to B, there exists a B3 belonging to B, such a B3. So this is similar to that one, there is no problem out of this one. Alright. Now we come to the next stage of generating, and then only I will use the word generating here. Exactly similar to what we did in topology. Okay, what is the next stage? Subbase. What is a subbase? Let us define. A subfamily S of Px is called a subbase for a filter if and only if the family of all finite intersections of members of S forms a base. You understand? You see, there is no condition of finite intersections and so on that was taken care by this condition on the base. Now starting with arbitrary family S, okay, that will be called a subbase. This is a definition now for a filter F if and only if the family of all finite intersections form a base. In this case, we say S generates F,
Sir,
or equivalently, F is generated by S. Okay? Yeah, tell me.
sir, this condition that family of all finite intersections form a base, this automatically implies that every that empty set cannot be in the S.
Empty set can be there. Empty set will not be there, but the family may be empty. Empty set will not be a member of this one at all, because if empty set is there, then it will be there in the base also, right? But it cannot be a base, because once it is in the base, it will be in the filter also. So that is not allowed.
And this S also cannot be empty set, right?
S can be empty. Why? Because what is the finite intersection of members of S? Members of an empty set.
That will be complete X.
Whole X's will be there. Once X is the only thing now. Okay? Singleton X forms a base for what? Singleton X.
So
So,
if S is empty, then we will get our smallest.
smallest filter. The smallest filter has two bases, sub-bases. Empty set is a sub-base. Singleton X is also sub-base, but it is a base. Singleton X is the whole space also. Okay. Singleton X is not a sub-base. For sub-base we need non-empty families. Okay. Because once it is a sub-base, we are taking only supersets there. We are not going to take finite intersections there. So empty set is not a member of any base, whereas empty set can be a member of, empty set cannot be a member, but the family itself can be empty. Okay. So as you have pointed out, the finite intersection of members of S forms a base automatically implies that empty set is not a member. But this family S may have no members also, that is allowed. However, in practice, it gives you only the singleton X, right? Therefore, for all practical purposes, you can assume start with S as non-empty family, that's all. So, family S contained inside Px is a subbase for a filter if and only if S has finite intersection property. Once again, you may be confused. If S is empty set, it has finite intersection property, because the only family which is finite family is empty family there. The empty family intersection is the whole set. That is not non-empty. Okay. So now we will do little more with functions. This is again similar to what we did in topology. Start with any function from one set to another set. S be a subbase for a filter f on X. Then I want to push it to Y. How do I push it? Take f of S, curly S, equal to all fa where A is inside S. So this is a subfamily of Py, right? If S has some elements there, then Fa will have some elements. All right. So this family is a subbase for a filter, and that filter will be denoted by f check of F. Okay. So how do I do that? What is the meaning of subbase for a filter now? Take finite intersections of members of Fs, then take all the supersets. So that is your f check of F. All right. So all that I have to see is that this family has finite intersection property. If you take FA1, FA2, FAN, intersection is f of A1, A2, A1 intersection, that will be contained inside that one. So that is non-empty, that's all. Notice that the family FF, okay, namely, if you take S instead of S here, put F, the whole F, where F is a filter, okay. FF, such as FA is inside A, fails to be a filter on Y in general. Okay, what we have done? You take a subbase and then this will be a subbase for a filter. It may not be a filter in general, because there may be bigger subsets which don't come from S at all, right? Bigger subsets which don't come from even F. So if you take FA such that A is inside F, this may fail to be a filter. Okay. However, if you take F check of F, that contains the family FF, because what is the meaning of F check of F? F check of F, treat F as a subbase for F itself, right? Then F check of F makes sense. So this contains FF, that's all. This is similar to the situation of push-outs of topology. Same thing we have done for topologies also. If you take open subsets of X and then take their images, okay, that may fail to become a topology. But unlike in the case of topologies, pulling back filters, going the other way, okay, where it was nice in the case of topologies, pulling back filters under arbitrary functions does not work here. Remember, if Y is a topological space, there is a topology, X is some set, and F from X to Y is a some function, then I can take inverse image of open subsets in Y. They themselves form a topology on X. That was a nice situation for it. Here it doesn't work. Not only that, we don't need it at all. Okay. So even it's worse than that. Namely, even the family F inverse of B, where B is S prime is a subbase. So okay, this may not satisfy the finite intersection property. So of course, if we assume F is surjective, then this works. So you have to assume more and more hypotheses. So let us not bother about, because we are not going to use it in the convergence theory of filters, which is our aim after all. Okay. So this is what I mean by saying that basics of filters, that's all. Next time we shall now study seriously its relation with topology, namely convergence theory for filters. Okay, thank you.